Hello, everyone. I'm Chi-Ning from Harvard. Today, I'm going to talk about our joint work with Madhu, Santhoshini, and Sasha on the approximability of all finite CSP with linear sketches. So this project is about the unconditional hardness of approximating constraint satisfaction problems in the streaming model. So all this buzzword will make sense in a minute, but just to give you a punchline of the result, we characterize the optimal approximation of all finite CSP in certain streaming models. So let's start with some basic definitions. What is a constraint satisfaction problem? Let me define this with a running example of max cut. So in a max cut problem, we have an undirected graph G as an input. We have lots of edges. And the goal is to bipartite the graph into two parts. And we use variable x1 to xn as a Boolean variable 0,1 to denote which part it lies in. And now an edges is modeled as a constraint of the form like it is only the value of the constraint is 1 if and only if the two sides of the variables are assigned differently. And now the input undirected graph is then modeled as a bunch of constraints for each edges. So that now the goal is to find the largest cut becomes to finding an assignment to the variables that maximizes the number of satisfied constraints, which is corresponding to the number of cut edges. And formally, it is defined as the following equations, just the number of constraints being satisfied. So constraint satisfaction problem is ubiquitous, and not only max cut is captured by it, lots of problem it is too, and is extremely well studied. In particular, in the case where we want to understand the complexity of solving CSP problem exactly, this is very well studied, especially by the seminal Schaeffer's dichotomy theorem. We know that for any Boolean CSP, if we want to solve it exactly, it is either in P or it is NP hard. So the understanding of solving Boolean CSP exactly is very well studied. And then people then wondering about what about solving CSP problem approximately? Because in practice, maybe we are happy with just having some max cut with good and not cut value. But how do we define approximating CSP? So intuitively, this means that we not necessarily need to find the optimal cut, doesn't need to achieve the optimal value. And but formally, how do we argue it? And it turns out that there are lots of different formulations. And here we pick the one which means thinking of approximation as distinguishing instances with different value. So formally, we said an algorithm achieve an alpha approximation for some alpha within 0, 1. It means that it can distinguish instances with value greater than certain value v, or no instances with a value strictly less than alpha times v. So to see why this definition makes sense, you can think of when alpha is being 1, this actually exactly corresponding to the exact problem to distinguish whether the value is v or strictly less than v. And when alpha is some 1 minus epsilon for some any constant epsilon, this corresponding to fully approximate the problem. So let's also use max cut as an example to get familiar with this definition. So on the algorithmic side, an easy random assignments sampling algorithm can already give you half approximation, meaning that you can find a cut just like a 0.5 away from the optimal cut. And Goldman-Williamson semi-definite programming-based algorithm can improve this to 0.878. And on the hardness side, if you assume NP hardness, you can show that 0.941 cannot be achieved by any point number time algorithm. And if you believe in unique game hardness, this can be further improved. So in this area of approximating CSP, there's lots of fascinating results, and there's also lots of open problems. But before, like recent years, usually the focus is on the polynomial time region, meaning that like a harness is based on NP harness of unigame harness. And today, in our project, we are going to focus on the unconditional harness of approximating CSP. In particular, we are going to study the unconditional harness through the lens of streaming model. So let me define what do I mean by CSP in the streaming model. So now, rather than a polynomial time Turing machine, we consider a bounded space machine, namely only have sublinear or even logarithmic space. And now the CSP constraints comes in the stream, and the bounded space machine has to somehow remember it, and then tell us like something about this CSP instance. So note that the input arrives in string once, so the machine cannot store the whole input. Furthermore, it even cannot store the whole assignment, because the assignments essentially take omega n space. So for sublinear space streaming algorithm, it even cannot store an assignment. So we need to slightly adjust the criteria a little bit. So when we call an alpha approximation, we ask the streaming algorithm to output an integer v, which satisfies the soundness criteria, meaning that there should exist an assignment satisfying v constraints. Also have the alpha approximation guarantee, meaning that v cannot be too small, because if you always output 0, it's always satisfies soundness, but you want this to be large as possible. So we want it to be, say, greater than alpha times the optimal value. This is like a approximation guarantee. So we call a streaming algorithm being an alpha approximation. It means that we can analytically show that there exists an assignment having v, and v is not too small. So just to give you an example of max cut again. So it turns out that the trivial random sampling algorithm gives you half approximation in the following way. So after receiving lots of edges, the streaming algorithm simply output the number of edges divided by 2. So note that because the algorithm only count the number of edges, so this can be easily done by like a logarithmic space. And also a simple expectation / probabilistic analysis. We can show that a random assignments indeed satisfy this number of constraints. So we know that a random cut has a value, number of edges divided by 2. It means that there exists a cut having such value. So this is saying that this algorithm satisfies soundness criteria. And half 1/2 will become your approximation ratio. It turns out that this trivial random sampling algorithm actually is optimal for streaming model. In particular, after a bunch of work culminating at this Kaprilov-Kirchhoff paper in Stock 2019, they show that even to achieve, slightly improves this 1/2 approximation by epsilon for any constant epsilon require linear space. And as a comparison, in the polynomial time region, you can actually do slightly better than this. So other than max cut, recently people also study a lot on the approximability of a CSP problem in the streaming model. In particular, today I'm going to focus on a recent result on characterizing the approximation ratio for any finite CSP. But just also let people know, although we characterize all these CSP, there's still a lot of graph problem or other problem interesting in the streaming setting. So to state our result, let me first give you an informal statement and try to state the formal version later because it requires some stuff. So we characterize the approximation ratio for every finite CSP, meaning that finite CSP means that we fix a constraint family. Your constraint function can only come from a finite set. And we consider a slightly weaker streaming setting called sketching algorithm. And for more details, please visit our paper. But for some technical issue, we can only focus on that. But to justify the choice, most of the streaming algorithm norms in most of the applications, they are actually all of the form of sketching algorithm. So now to state our classification theory, we show that for any finite CSP, there exists an alpha such that Slightly less than alpha, we can show you there exists a linear sketches algorithm in a polylogarithmic space. And slightly above alpha, then any sketching algorithm requires square root of n space. So more detail will be stated later, but in the next few minutes, I'm going to give you a rough sketch on like how do we prove this theorem and how to formally state this theorem. So the roadmap for the rest of the talk is to first formally say our classification theorem, and then have an overview on how to prove the harness and the algorithm. And we are going to conclude with some future directions. So due to time limit, I cannot talk too much detail. So hope this talk just give you like a starting point to be able to read our paper. So our classification theorem. So before stating it, let's motivating the analysis a little bit by a previous work who studied max directed cut. So rather than outputting the number of edges divided by 2, in the study of max die cut, people look at these things called the bias and total bias of a directed graph. So now the bias of a vertices is defined as the difference between in and out degree. And the total bias is just the summation of the absolute value of all the bias. So what they can show is the following. The previous work showed that given certain total bias, they're actually having some cut value that cannot be achieved by any graph with this total bias value. Namely, they can characterize this blue line as an upper bound of the cut value given a total bias value. And they also can establish some lower bound, saying that, oh, having this certain bias will guarantee your cut value to be at least these things. So this analysis already immediately gives you a streaming algorithm if you can estimate total bias in small space. And indeed, this actually can be achieved by standard streaming techniques. So what they do is simply output the lower bound line after estimating a total bias. And then the approximation ratio of this algorithm will simply be the ratio between the upper bound and the lower bound, because we know that the optimal cut value cannot be greater than the blue line. And in the die cut case, this ratio turns out to be 4/9. So this idea of total bias actually can be generalized to like a problem beyond die cut, can be generalized to other CSP, but how can we generalize it? So in hindsight, this framework of proving both upper bound and lower bound is by identifying certain distinguishing statistics. So in the case of die cut, this distinguished statistics is the total bias of a graph. And for other case, you might have some distinguished statistics mapping some CSP instant to other stuff. But we can first take a look at what kind of property we want from the distinguishing statistics. On the algorithmic side, we want this distinguished statistic to be easily estimated in small space when receiving input. And we also want this distinguishing statistic can tell us something about the best possible achieved CSP value and the worst possible value. So in the die cut case, it's like your distinguished statistics, you can characterize the upper bound line and the lower bound line. And you want this characterization to be as tight as possible. And the largest ratio among the upper and lower bound will then be the approximation ratio. And on the harness side, in order to show this upper and lower bound is tight, the idea will then be establishing some distributions of input instances that matches the upper and the lower bound. For example, in this case, if we fix the bias or fix the statistic value to be 1, we want to establish 2 input instances, one on the upper bound line, we call it yes distribution, and another on lower bound line, we call it no distribution. And we want them first to having value achieve the line. And second, we want them to be indistinguishable for streaming algorithm with small space. So that's the high-level idea underlying this kind of framework of using distinguishing statistics to understand the approximability of CSP problem. But then the question would be how to systematically find the desirable distinguishing statistics. So at first scan is unclear. In particular, previous die-cut things using some combinatorial property, how can we in general find the distinguishing statistics for any CSP problem? So our idea is to generalize the bias idea from just a bias value using the bias vector defined for each vertices to a bias matrix. So we consider any possible sketching metrics to define a bias matrix, and we use the norm, certain norm of the bias matrix as a distinguishing statistics. And the second idea would then try to use this information to generate instances distribution satisfying matching the upper and lower bound, which in the meantime still indistinguishable. So there involves some technicality to really match the two work, but in hindsight, the idea is to match the sketching metrics and the marginals that you can generate distributions. And for more detail, I encourage you to read our paper. And in the hindsight, this marginal or this sketching metrics will then help us define two sets, two convex sets. One is called the yes convex sets, denoting the marginals of distribution that can have larger CSP value, and the no convex sets corresponding to the marginals with distribution having CSP value at most something. So now to state our classification theory, it actually can be characterized by the two convex sets mentioned before. So if the two convex sets is intersecting, it means that for this to distinguishing value from greater than gamma and smaller than beta, it actually can be solved by linear sketches. So if these are disjoint, then you have the algorithm. But if they intersect, we can show that then there cannot be any sketching algorithm with space less than square root of n. So again, I encourage you to look at our paper for more details. And for the rest of my talk, I'll just give 1 minute sketch for the harness and algorithm side respectively to convince like why this intuitively makes sense. So on the harness side, when they are intersecting, we want to show it is difficult, and we use the standard way of communication complexity to prove it. So the high level idea is like usually when you have a streaming algorithm, you can use the configurations of the streaming algorithm to design the protocol for the communication game. So the space consumed by streaming algorithm will upper bound the communication complexity. So if you can prove communication lower bound, then you have a streaming lower bound. So basically, we are just like using some standard communication problem called Boolean hidden matching problem and design a bunch of reductions and then result in our streaming result. So yeah, in our paper, we also have a figure trying to explain all the reductions. And on the algorithmic side, we want to show that if they are disjoint, the two sets are disjoint, then there's algorithm. And the high level idea just like, since they are all convex, so if the two sets are disjoint, that means that there's separating vector. So the idea is just use this separating vector as the sketching matrix we mentioned before. And then we use a certain norm of the matrix as a distinguishing statistics. And up to some analysis, which actually is quite standard and straightforward, we can show that this algorithm actually already works. So to conclude, we show a dichotomy theory of approximating CSP in the streaming model, especially like for sketching metrics. And basically the idea is to identify the convex set is the right way to look at approximating CSP in the streaming model. And indeed, I skipped lots of details, and but what I said previously should already give you an overview on how to read our paper. And let me summarize with some future directions. So first, in our paper, we only focus on single pass input, and it is quite interesting to consider multi-pass. And also, our lower bounds only hold for square root of n space. Can we go beyond to linear? And also there's some caveat on the setting. Can you improve to a more general setting? And also it will be interesting to see if there's application of our theory. Yeah, so that's all I'm going to say today, and thank you for your attention.